Hello everyone, I'm Charles Cagayo. I work at Bristol University and today I'm going to discuss about the design process for 4D printed composite macroscopic bending hygromorph. So I work under the supervision of Fabrizio Scarpa and I would like to thank DSTL for sponsoring my PhD. So I've been working over the past years on the design process for continuous flux fiber reinforced PLA hygromorphs. The question that comes the most when I present this work is what are the application for that kind of structures. It's always a bit tricky for me to answer because in the field of engineering there have not been a lot of commercially available application for that kind of structures. The idea of the presentation is to humbly highlight steps in the design process which could benefit from improvement or inspiration from other fields of engineering in order to propose more application for that kind of structures. Example of such structures would be solar tracker. For instance, a solar tracker which would deforms in order to follow the path of the sun without any energy input, but also self-monitoring building, in which the humidity inside the building would be tailored without energy input. So this work is mostly based on literature review and not on my specific lab work, and I'm mostly going to describe what exists and what research could be conducted in this field of engineering. So the first thing I want to discuss is the definition of 4D printed. So in the 4D printing, the three first dimensions refer to the production of a part via additive manufacturing techniques. And the fourth dimension refers to time, and especially to the transformation of the printing part occurring if the part is placed in a specific environment. An example is given on this slide. On this video you can see an example of a 4D printed structures. It's a 3D printed continuous flux fiber reinforced PLA parts, which transformation is actuation, so bending actuation, when the environmental humidity is modified around it. So basically this part was conditioned at low humidity and then immersed in a high humidity environment, and you observe the actuation on the video. So to give a bit more context here, I'm going to explain what I'm going to discuss in here. So we're only going to talk about composite materials, material made of two different materials, material 1, material 2, which are only assembled in 3D printing. There are other ways of producing 4D actuators, but in our case we only consider printing. And we're going to condition it in a relative humidity RH and no other any conditioning trigger which could be used. And the only actuation we're going to look is the bending actuation. So basically most structures which respect this definition are made of different layers with different humidity expansion coefficients, and therefore when these layers want to expand differentially, then there are stresses created at the interface of these different layers and therefore actuation. So to summarize, in this presentation I'm going to talk about 4D printed parts at macro scale, only composite materials, and environmentally humidity stimuli structures. So we're going to look at how the different parts in the design process of this element could be implemented, and we're going to humbly describe what could be done in order to propose more commercially available applications for that kind of structures. When we conducted the literature review, we realized that the study discussing the material and the structures that I've just described usually fit into one of the three categories. The first one is what we call material actuation capability. It's basically when you want to prove that your material is capable of actuation. What you usually do is print a visually satisfying structures, for instance a flower, then you immerse as I explained, and then you observe the actuation, proving that your material is capable of actuation. Then there is actuation controlling parameters, is when you select one parameter or more than one, and then you change this parameter and see how this influences the actuation that you observe at the end. And finally, what we call lab applications is basically trying to foresee what could be the final application for that kind of structures. And one of the most common one is a hook. So basically you have a grip which will, because of the be immersed in water, and because of the actuation it will hook an object, for instance a ball in this case, and then you can grip it out of the water. And so what we want to do in this is to look humbly how we can improve these three different types of techniques in order to be able to propose more commercially available applications. So the first thing to do in order to do this is to look at how to measure the actuation. There are different parameters that have been used in past study in order to account for the bending actuation that we want to describe in here. The first category of parameters that we've been able to observe are global parameters. So it's, for instance, in here, kappa is a curvature, eta is the deflection, and it's basically parameters which are capable of accounting for global deformation of the structures. These parameters are very efficient if you want to vary one parameter and see how this influences the general deformation of these structures. However, they have two issues. They do not fit perfectly the shape of the material because, for instance, there is an inherent error when you fit a circle on your specimen after actuation in order to measure the curvature of this circle. The circle will never fit perfectly your specimen, and this creates an error. And the other thing is that it's a limiting parameter in the sense that it cannot uh, um, uh, observe complex deformation of the structures. It's only if you have one global deformation in one direction, then you are able to account for it. And that's why researchers are increasingly going for local parameters, which are able to measure local deformation of the structures. On the left side of the screen, you can see in the light blue displacement, and in dark blue the position of the structures. Basically, you position little points along your specimen, and you see how those little points deform or move in space. And so, as you can understand, there are different parameters that are used to account for actuation, and it would be interesting to know which are the most efficient and which would be suitable for one particular type of actuation or another one. So the second thing I want to discuss is the type of structure which are available to create that kind of actuation. We've been able to observe three different categories of such structures. So continuous fiber hygromorphs, which are, for instance, continuous flax fiber reinforced PLA, so the one that I've been implemented. Short fiber hygromorphs, which are wood chipped with PLA, for instance, or polypropylene, and multi-material, which are materials which are usually considered as isotropic, and it's the distribution of this material which create different actuation between the different layers. An example of this is hydrogels or elastomers. For the short and continuous fiber, it's a bit different because the materials are intrinsically orthotropic and strongly orthotropic, and therefore it's the fiber path between the different layers which will create the difference of actuation between the different layers, and therefore the actuation. So it's interesting to know that in general ways, it's not always the case, but general way, if you go from the right to the left, you'll have greater mechanical properties. But if you go from the left to the right, you'll have more flexibility in terms of productions. It's also worth noting that the continuous fiber hygromorphs is a very new field of application, and it could be very interesting to work a bit more on this in order to be able to obtain multifunctional structures capable of carrying loads, but also actuating. And there is a lot of work in order to be able to make this more flexible in terms of production. So now that we know what kind of structure we can use in order to obtain actuation, we want to know how to create this actuation. So it's a two-stage process in which you have a reference stage. So it's a stage in which you have your specimen and you condition it at a specific humidity, and you wait for the humidity to be homogenized inside it, and then you transfer it to an actuation stage in which the humidity is modified, and therefore this modification creates the actuation of the structures. So we've been able to detect 5 different ways of obtaining this two-step actuation: air, oven, water, passive desiccator, and active desiccator environments. The most widely implemented is air to water and water to air. For sake of simplicity, it gives a fast actuation and a large amplitude of actuation, but it has some interesting problems. The first one is that there is only one humidity available to that kind of structures. And the second one is like air is difficult to know what air is. What is the relative humidity of air? It depends on many things, where you are on Earth, at what time of the day you are, and so it cannot be trusted in terms of repeatability for tests. And that's why researchers are going increasingly for passive desiccator or active desiccator. Passive desiccator is a box in which you have a specific relative humidity, and you cannot modify this relative humidity unless you open your box. The active desiccator is capable of modifying the humidity inside the box without opening it. And so there are plenty of ways in order to create this actuation, and it would be interesting to know what would be the most efficient relative humidity in order to be able to have repeatability of test, to be able to compare different materials, but also relative humidity which could be representative of further application inside or outdoor applications. So when you select the way you measure you create your actuation, you have to account for the way you're going to measure your actuation. And there are 3 different types of categories that we've been able to highlight for the measurement techniques for actuation. The first type is physical measurements. It's basically when you have a physical interaction with your specimen. A good example of this is a researcher who created a sort of a ruler with different curvature on it. And basically, depending on which curvature was fitting the most specimen, she would know what is the actuation, the deformation, the bending of a specimen. Another technique, and the most widely implemented, are photos. Basically, when you take photos of your specimen and then you post-process it manually or automatically, usually using Fiji or ImageJ. So it's very widely implemented if you want to have a global deformation of your structures. You take an image, then you plot a circle around your specimen, and then you measure the curvature of this circle. And the last technique is what we call point of interest. It's basically when you position little point of interest on your specimen, and then you take a video and you track the position of this point of interest through space, and then you obtain the parameter that you want, a curvature or a deformation or a displacement, depending on the actuation that you get from your video by post-processing it. And so you can see that there are many ways of measuring the actuation, and this would be very interesting to know what are the best techniques depending on what type of study you conducted and depending on what type of conditioning you conducted, in order to be able to compare a bit more materials So there are different parameters which could be measured for actuation and which could be used in order to compare the different materials and structures for actuation, for instance the speed. I want to discuss about one of the most important for applications, which is reversibility. So the way it works is that you have your structures, you immerse it in a specific relative humidity, in that case alpha. You measure its deformation through kappa I in that case. Then you give it what we call an actuation history. That means that you condition it for N1 relative humidity, for N2 repeats, and during N3 hours, days, or whatever the time you want this repeat to occur. And then you make a reversible test in which you condition it at the same humidity than at the beginning and measure again this deformation. And then you compare kappa F to kappa I, and you see what are the difference between the two and if this technique is capable of reversibility. So yes, we can understand from this explanation there are basically an infinite number of tests which could be conducted, and it would be interested for a researcher to know which are the tests which would be the most relevant in order for further application in different conditions, and which are the best tests to conduct in order to compare different materials for different reversibility capability. Especially because we are considering composite materials, and which composite materials means interface between different materials, and usually this interface could be problematic, especially regarding humidity conditioning. So here I'm going to discuss about the modeling for that kind of structures. There are different scales of modeling for 4D printed hygromorphs. The first one is a layer scale. So as I said, the actuation is happening at because the difference between the actuation capability of different layers, and therefore modeling at the layer scale enables to have a very quick and global understanding of how the material is going to deform. So 2 ways of doing this is a widely implemented Timochenko beam theory and the classical laminate theory. This is widely implemented in order to modify one parameter and see how this parameter impacts the deformation of the structures. For instance, the thickness of the one or the other layer. The other layer is called the phase scale, which is often connected with finite element model and elastic energy based model. So this distinguishes the different materials that we are using as composite materials. So in terms of fiber composites, so short or long fiber composites, it will usually be orthotropic filament scale deformation model, which is being implemented. Whereas in multi-material, it will often be like blocks of one material or the other, which are distributed differently in space. This scale is very efficient for optimization of the distribution of material in the different for the different types of hygromorphs discussed here. So if we are talking about modeling, we must talk about how to measure the properties. So in the paper, we discuss about different ways of measuring the properties. We present different decision trees in order to know which property to measure depending on the structures that you are considering and the scale of modeling that you're considering. For the mechanical properties, it's fairly straightforward because all the standard and literature is available today. But we even propose a long and short fiber composite comparison in order for the different materials which are available to create that kind of structures. One thing that we want to emphasize is the importance of understanding the impact of humidity on the material, because sometimes the hygromorph actuation will be fairly long, and therefore this will impact the humidity. The mechanical properties, the humidity will impact the mechanical properties during the test, and understanding this impact will enable to understand the comparison between the model and the real hygromorphs. Another thing which is very important is the expansion properties of the material. So here's a decision tree, again depending on which type of material you're considering and which type of scale of modeling you're considering. The standardization is not as significant as for mechanical properties. For instance, researchers have been using micrometer and calipers a lot, but this technique is slowly going down for microscope to emerge, and they use more and more optical measurements in order to account for this property. The expansion property, which is the ability of the material to deform in different directions, also depend on the shape of the specimen implemented, and it would be interesting to know which are ideal shapes in order to measure these techniques. And finally, there are different types of parameters which are used in order to account and to measure this expansion capability. For instance, I use coefficient of moisture expansion, others use hygroscopic drain, others use volume changes. They all mean the same thing, but making knowing which would be the most efficient in order to account for this deformation capability would be an efficient way of comparing different materials and predicting the deformation of the structure. So finally, I want to discuss a bit the conclusion of this study. So if we want to implement more the type of hygroscopic 4D printed composite structures, then different things we thought could be interesting to conduct. The first one is temperature influence. So as I said here, we've only focused on humidity triggered actuations and the impact of humidity on the actuation. But actually there are other parameters, and the most important probably is temperature. There's been a lot of work conducted on temperature separately, and it would be interesting to mix the two kinds of influences in order to know which would be impacts what, and to precisely control the actuation of the structures. The second thing is to improve that kind of structure that we've been discussing. So the reversibility is a big axis of improvement, especially because, as I said, we're using composite materials, so interfaces. It means interfaces are created which are very sensitive to humidity. The other thing is multifunctionality. So I've been saying that continuous fiber composite could provide good multifunctionality in terms of mechanical properties and actuation, but it's a fairly recent research area, and more work is to be conducted. And an aspect I have not discussed, but we discuss it extensively in the paper, is the optimization of the distribution of material and optimization of parameters for printing that we discuss, especially the impact of neural networks, which has been used extensively for multi-material structures, and also how we can be inspired by compliance optimization, especially for continuous and short fiber composites definition. This is a big aspect of the research, which we invite you to have a look if you're interested in the literature review that we've been conducted. And the last thing is the control and standardization of the different parameters. As I did extensively in this presentation, how to define between global and local parameters, which are the best conditioning techniques in order to have something representative of potential further application, but also which could help comparing different materials, especially depending on different parameters, for instance, reversibility or speed. So I would like to thank you for your attention and listening to my presentation. I would like to thank everybody who took part in this work, Frederic, Antoine, Adam, and Fabrizio. All this work is available in the design of 4D printed hygromorph state-of-the-art and future challenges. There are far more things that we discussed in there. I've just made a quick introduction through this presentation. I've added here my email address. Feel free to contact me if you need any practical details for you creating your hygromorphs, or if you need design advices. It would be a great honor for me to answer any of your questions. Thank you.